We presently view the nature of the universe very differently than did our ancestors. Throughout most of human history, it was believed that there was one set of principles which applied to the events that happened here on Earth, and a very different set of principles which governed the rest of the universe. The behavior of the stars and planets, which were thought of as the heavens, were seen to be fundamentally different from the behavior of objects in our everyday lives here on Earth. This view of the universe changed forever with the theories of Isaac Newton. Isaac Newton believed that there were 3 laws of motion that applied to all objects here on Earth, and that also equally applied to all objects everywhere in the universe. According to Newton, the gravitational force here on Earth, which caused objects to fall to the ground in our everyday lives, is also the exact same gravitational force which caused the planets to orbit the Sun. In Newton's view, there were no longer 2 different sets of laws that applied to the heavens and to the Earth, but one set of laws that applied to all objects everywhere. There is another story very similar to this. We once had a set of laws for magnetism and electricity, which governed the behavior of magnets and the flow of current through a wire. And we had another very different set of laws for optics, which governed how light passes through lenses and bounces off mirrors. Then, James Clerk Maxwell came up with the theory that light is actually just a wave of electric and magnetic fields. Maxwell's laws consisted of just one set of rules that not only explained all of electricity and magnetism, but also explained all of optics and the behavior of light. Throughout history, regardless of the subject matter, this pattern has been repeated time and again. The more our knowledge advances, the greater the number of seemingly unrelated phenomena we are able to explain using fewer and fewer laws. This has led some people to speculate that perhaps one day we will discover just one set of laws that are able to explain all phenomena everywhere in the universe. We now know that Newton's theory of gravity and Maxwell's laws of electromagnetism are actually incorrect. According to general relativity, gravity is not a force, but is due to the fact that objects with mass cause a curvature in space-time. According to quantum mechanics, electric and magnetic fields do not actually exist, and light is composed of particles which we call photons. According to general relativity, objects moving in straight lines through curved space-time appear curved to us, creating the illusion of a gravitational force. According to quantum mechanics, photons exchanged between charged particles create forces, thereby creating the illusion of electric and magnetic fields. The predictions of Newton's law of gravity are now explained by Einstein's general theory of relativity, which also explains many additional new phenomena, such as how gravity affects the flow of time, and the existence of black holes, where time seems to stop completely. Similarly, the predictions of Maxwell's laws of electromagnetism are now fully explained with quantum mechanics, which also explains many additional phenomena, such as the photoelectric effect, quantum tunneling, and the behavior of atoms and molecules. Newton's law of gravity and Maxwell's laws of electromagnetism appeared to be correct to us only because their predictions gave very good approximations under most of the conditions that we were typically able to observe. In exactly the same way, it is possible that general relativity and quantum mechanics are similarly also only approximations to the true fundamental laws that actually govern the universe. If this is the case, could this one true set of fundamental laws of physics provide us with a single unified explanation for everything in the universe? There are some people who believe that everything in the universe, including human societies, are composed of atoms and molecules which behave in accordance to the laws of physics, and that the fundamental laws of physics are therefore responsible for the probabilities of every phenomena in existence, from the flow of human history to the details of our individual lives. However, there are many other people who strongly disagree with this view, and who believe that there are some phenomena in the universe, such as the consciousness of the mind, which can never be just the product of atoms and molecules behaving in accordance to physical laws. In any case, regardless of which point of view is correct, even if the fundamental laws of physics are not literally responsible for the behavior of everything in the universe, they are still nevertheless responsible for the behavior of a very large part of the universe, if not the entire universe. We presently already know how to explain many biological processes entirely in terms of the underlying chemical reactions inside the cells. And we already know how to explain many chemical reactions entirely in terms of underlying interactions of the atoms and molecules, which behave in accordance to the known laws of physics. Therefore, when we study physics, we are studying the foundation of chemistry, biology, and everything that exists and that will ever exist in the future. Or, at the very least, almost everything. It is possible to get through life without ever studying physics, as human beings created magnificent works of architecture and engineering for thousands of years before anyone ever heard of Isaac Newton, James Maxwell, or Albert Einstein. And there are many cases where viewing a phenomena in terms of the laws of physics can actually take us further away from understanding it. As one example, a computer is based on the operation of logic gates, which have inputs and outputs that can either be logic high or logic low. These logic gates are based on the operation of transistors, and the operation of these transistors is based on the laws of quantum mechanics. The problem, though, is that even if we are fully aware of everything we can know about the position and momentum of all the particles inside the transistors through the laws of quantum mechanics, we may still completely miss the logical meaning that the circuit signifies. This is the same way in which a detailed analysis of the atoms and molecules inside a neon sign will never tell us that the sign spells Joe's Diner. Nevertheless, if we never study physics, then we are at a significant disadvantage, even for the tasks that we think that we already know how to do. As an analogy, suppose we need to be able to add two numbers together. One approach is to try to memorize the sum of every possible combination of numbers that we will ever wish to add. This approach may work if there are only a few combinations of numbers that we care about. But this approach becomes more and more difficult as the amount of numbers that we care about increases, and we will never be able to memorize every possible combination, since there are an infinite amount. Fortunately, there is a second approach to this problem, and this is to learn the rule for long addition. Once we learn this fundamental rule, then we will always be able to add any two numbers together, even if we have never seen them before. In exactly the same way, there are many fields of knowledge where people have spent a lot of effort trying to memorize every new scenario and piece of information that they encounter, when they can accomplish far more by just learning and understanding a very small number of general principles. Once the general principles are understood, all the other principles can be derived from them. And the most general principles of the universe are the laws of physics and mathematics. It is only the study of the fundamental laws of physics which made possible many technologies that were unimaginable to our ancestors, but that we now rely on in our everyday lives. As was discussed earlier, all computers and digital electronics are based on the operation of transistors, and the development of transistors was possible as the result of an understanding of quantum mechanics. As another example, global positioning satellites can operate properly only by taking into account the equations of general relativity for how gravity affects the rate at which time flows. There is another important reason for learning about the fundamental laws of physics that go well beyond their practical usefulness. Curiosity about the nature of the universe we live in. And this curiosity may take us to discoveries far beyond our wildest imaginations. As an example, Newton's laws accurately predicted the behavior of objects here on Earth, such as the trajectory of cannonballs, and his laws also accurately predicted the orbits of the planets. All planets except for two: Uranus and Mercury. Uranus had irregularities in its orbit that deviated from what Newton predicted. It was then theorized that these irregularities may be due to the gravitational attraction on Uranus by other planets beyond Uranus's orbit that had not yet been discovered. Calculations were performed, based on Newton's law of gravity, to determine where the location of such a new planet would have to be in order to explain these irregularities in Uranus's orbit. When the telescopes were then pointed in this direction, they did indeed discover a new planet, exactly where the calculations had predicted. The planet was named Neptune. The ability of Newton's theory to predict the existence of a planet before it was even observed was an accomplishment that had never been done before in all of human history. This was therefore seen as further confirmation that Newton's law of gravity must be correct. But there was still the issue of Mercury. Nevertheless, just as an explanation consistent with Newton's law of gravity was found for the orbit of Uranus, it was believed that one day in the future, a similar explanation would be found for Mercury. The world waited patiently for this explanation, which never came. At the beginning of the 20th century, for reasons completely unrelated to the orbit of Mercury, Albert Einstein developed the general theory of relativity. Einstein's theory was able to make all the same correct predictions that Newton's theory was able to make, but unlike Newton, Einstein also correctly predicted the orbit of the planet Mercury. Einstein's theory of general relativity didn't just make better predictions. It stated that the true nature of time and space are far more mysterious than anything any science fiction writer has ever been able to come up with. For example, Einstein's theory of relativity states that there is no universal moment of time called now that everyone can agree on. Different observers can disagree on whether or not two events happened at the same time, and no observer is more correct than any other. Two different observers can also each believe that the other person's clock is running slower than their own, and they would both be equally correct. And both observers would be equally correct in believing that they are standing still, and that the rest of the universe is moving around them. The predictions of general relativity have been tested numerous times in many different ways. For example, atomic clocks in orbit have been compared to atomic clocks here on the ground, and the decay times of particles moving relative to us at near the speed of light have been compared to the decay times of particles which are at rest relative to us. The results of the experiments have always been exactly what Einstein's theory predicted. But just as Newton's theory was not initially able to fully explain the behavior of Uranus or Mercury, There are also two phenomena that Einstein's theory is not presently able to fully explain. We have called these two phenomena dark energy and dark matter. Dark matter deals with the fact that the amount of matter we are able to observe in each galaxy is far less than what it would need to possess in order for gravity to hold the galaxy together, given the galaxy's rate of rotation. Dark energy deals with the fact that the rate of expansion of the universe is accelerating rather than slowing down as we would have expected. Perhaps these two phenomena may one day be explained similarly to the way that the orbit of Uranus was explained. Uranus's orbit didn't really violate Newton's laws, and it was simply necessary to take into account the presence of another planet, Neptune, that we previously didn't know about. Similarly, the existence of dark matter, for example, may simply be due to the presence of subatomic particles that we didn't yet know about, and Einstein's general theory of relativity would not be violated. On the other hand, it could also be that dark matter and dark energy are instead analogous to the orbit of Mercury. The orbit of Mercury was evidence we had all along that Newton's laws of motion gave an incomplete picture of the true nature of time and space. Similarly, dark matter and dark energy may be evidence already in our possession that the true nature of reality is far more remarkable and even far more mysterious than anything we can presently imagine within the confines of general relativity and quantum mechanics. For example, one of the possible theories behind dark matter is that its effects are really the result of parallel universes that don't interact with each other in any way other than gravity. The matter in the parallel universes would be gravitationally attracted to the matter in our universe, and hence the galaxies of nearby parallel universes would tend to form at the same locations as the galaxies in our universe. The gravitational attraction from the galaxies in these parallel universes would cause our galaxies to appear to us to have more mass than they really do, which corresponds to what we can presently observe. All the different universes together would constitute what would be called a multiverse. Each planet in our universe has a different climate, but all of them are subject to the laws of physics of our universe. In exactly the same way, it is possible that different universes have different laws of physics, but that they are all subject to a new set of fundamental physical laws that govern the entire multiverse as a whole. Just as only a tiny percentage of planets in our universe have climates that are suitable for life as we know it, it could be that only a tiny percentage of universes in the multiverse have laws of physics that are suitable for life as we know it. Though the existence of life does not necessarily have to be limited to life as we understand it. The multiverse may give rise to forms of intelligent life so diverse that none of them would ever be able to imagine any of the others. All of this is pure speculation, as we presently have no observational data of other universes. Nevertheless, it is good to keep in mind that although human civilization has existed for thousands of years, Newton and Maxwell formulated their theories only a few hundred years ago. And it is only in the 20th century that general relativity and quantum mechanics were discovered. We have come a long way since we believed that the laws of physics here on Earth were different than the laws of physics for the stars and planets. But we also still have a long way to go. Future generations may look back at our present understanding of the universe, much the same way we now look back at the view that the Earth is at the center of the universe, resting on the back of a giant turtle.